So let's imagine a new scenario where we have, what's the object going to be this time, kids? A bowl elephant. A bowl elephant. And let's put it on a skateboard. A bowl elephant is on a skateboard, and it has a Norwegian on top of it. Okay? So we have a Norwegian riding on top of a bull elephant on top of a skateboard. Now, what is the typical average mass of a bull elephant? 10 in kilograms, yeah. 100? Sure. It's a 100 kilogram bull elephant. What's the average mass of a Norwegian? Like 1,000 kilograms? 1,000 kilograms. I have a Norwegian in the classroom. That's why I'm making all the Norwegian jokes. Well, he claims he's Norwegian. I haven't actually seen a passport. So, he does have an accent, though, so he must be Norwegian. So the bull elephant and Norwegian, ooh, that's a good question. Let's say that the bull elephant / skateboard together are 100 kilograms. Thank you for the clarification. That was kind of important. So, and they are traveling this way at a velocity of 50 meters per second. How many sig figs you want, Henrik? 1, 2? No, let's go 2. All right. So, here's the fun part. Everybody ready? What's going to happen now is the bull elephant, and for those of you watching this video 50 years from now and wondering what is going on, the ball elephant is a private joke within the class. Right, class? Yeah. Work with me here. So, what's going to happen now is the elephant, is going to take Henrik and throw him with his trunk. He's going to take Henrik with his trunk. This is an elephant, right? Does that look like an elephant to you? A bull elephant? It's going to take Henrik and it's going to throw Henrik this way, that way, and that way. How fast are you going to throw him? No, that's crazy. Stop it. So the elephant is going to throw Henrik backwards at, I don't know. Let's go for 10 meters per second. Keep it simple. Okay? And the question that we're going to be analyzing here is, what is the final velocity of the bull elephant? That is the question that we're going to be trying to answer here. So, we're going to then use the conservation of momentum here. So we need to define our system. Our system is the bull elephant Henrik skateboard combination. So we're going to lump the elephant and the skateboard together because they're never going to separate. And so I'm going to call the elephant skateboard combination. I'm going to call that object A, and I'm going to call Henrik object B, or object H for Henrik. So what we know then is the momentum of the ball elephant skateboard combination plus the momentum of Henrik before he throws him is equal to those things sum after he throws him. Am I right? Am I right? Am I right? So let's figure this out then. Now we have, I believe, all the information we need. we can go through and start substituting what we know. So what is the momentum of object A, the elephant skateboard combo at 50 meters per second? What? 5,000 Newton seconds. I'm not going to bother with units here. They're all Newton seconds. That was 50 times 100. What is the momentum? Oh, crap. Yeah, that's fine. Of Henrik. It's fine. Normally we treat those as two objects, or as one object together, but it works this way also. What's the momentum of Henrik before? 1,000 times 50, which is 50,000. Nice job, Henrik. Nice momentum. So, again, like I said a second ago, remember earlier when the two things were stuck together, we treated them as one object? And we could have just as easily done that here. We could have said, oh, the ball is 100 and Henrik is 1,000. That's 1,100. 1,100 times 50 is 55,000, which is what we're getting anyway when we do it separately. So it doesn't make a difference whether we treat them individually or separately in this case. Now, afterwards, the momentum of object A is actually what we're interested in. There's no information in the problem about that, so we're going to leave it as a variable. The momentum of Henrik afterwards is, and be careful, what is the momentum of Henrik? Well, after the elephant has thrown him, what is his momentum? Well, it's the mass is still 1,000, but the velocity is positive 10 or negative 10? Negative. So negative 10,000. Okay. So all of this boils down to, if we simplify, we have 55,000 before equals the momentum of object A after minus 10,000. So what is the momentum of object A, the bull elephant, after? It's got to be 65,000. And that is in Newton seconds. And the question was, what was the velocity after? And so now we simply set that equal to m times v. And the mass of the bull elephant is 100 still. So we're going to divide it by 100 to get the new velocity. So the answer is 650 meters per second. Woohoo! I don't know if you're really picturing that quite, but that's awesome. 600. So he threw something backwards at 10 meters per second. And this is not necessarily intuitive the first few times you think of it. If you're on a skateboard going a certain direction and you throw something in the opposite direction, you're going to propel yourself faster in that same direction, right? Kind of like a rocket does. A rocket shoots exhaust out in the opposite direction of the way it wants to go. This is analogous to, remember a long time ago we talked about being out in outer space with nothing to push on, wanting to move. You chop off your arm and throw it in the opposite direction, right? Similar thing here. Same argument. Why not? Oh, so now why is this so ridiculously high? Why? 650 seems really fast. Why is it so fast? He only threw Henrik like 10 meters per second. But Henrik is it's a ton. Henrik weighs a ton, a metric ton, and so turns out to throw an object that's a metric ton at 10 meters per second, it requires quite a big impulse. So that works there. So there are a lot of other examples of problems. I think these are the only two I'm going to post on the web for now, and but they all kind of involve in various forms this idea of taking your system, setting up an expression for all the momenta of all of the things in the system, and realizing that before and after the change or collision, the sums are always equal. The individual momenta are not necessarily equal. The momentum of A or B or H, or none of them are necessarily equal, but the sum when you add them all together before should equal the sum when you add them all together after.